Hi, I didn't see you there. Simple harmonic motion, you say? Well, let's get this right underway. Simple harmonic motion is anything but simple. And, well, we wouldn't get anywhere calling it difficult harmonic motion, would we? So this is what hopefully you've come to terms with. The mass on the end of a spring. And what we're going to do is make a few definitions. So we're going to say maximum positive amplitude, maximum negative amplitude, and the equilibrium position being somewhere in the middle. And we're going to make reference to those three things throughout these explanations. So, up and down with a well-defined period. If I move on to the next slide, this is what you should have seen when you looked at the tracker software. So you should have seen displacement and time. And I'm just going to get another colour pen so that I can highlight some different things that happen on the graph. So we're going to start off with something that looks like this. So it starts off up here, moves down through the equilibrium position, to the bottom, up through the equilibrium position, maximum positive, and then back down to the equilibrium position, at which point I've run out of board. So I have to stop. There are interesting points here, here, here. These are all the same thing. At these points, the gradient equals 0. And hopefully you remember that the gradient of a speed-time graph, displacement-time graph, will give you velocity. Here, maximum negative, maximum positive. I can tell that because the gradient of the line is at its steepest. So I've ended up with something. If I replot it, the first point is going to be 0. The second point is maximum negative. This point is 0 again. This point is going to be my maximum positive, and this point is going to be 0 again. And if I draw on these things, I end up with something that looks like that. So, it's got the same period as the displacement time graph, but it is the derivative of the displacement time graph. And I end up with something that looks like that. Now, I could say that this is a cosine graph and this is a minus sine graph. If that makes sense to you, that is brilliant. But those are definitions of the derivative of each other. So cosine, derivative, minus sine. Now, hopefully, you might be able to predict what I'm going to do next. And that is to come up with the acceleration time graph. So if I keep my velocity time graph on the board, make it a bit cleaner by giving it some units, I can say here I've got a 0 gradient, here I've got a 0 gradient, here I've got a maximum positive, here a maximum negative, and here a maximum negative again, assuming that the oscillating mass doesn't lose or waste any energy. So what I'm saying is the amplitude of the displacement time graph that I drew on the board before, and the top graph on this set of slides doesn't change maximum or minimum amplitude. So up here, instead of displacement, we will have acceleration in meters per second squared, and this will be at 0, this will be our maximum negative, this will be our maximum positive, this again will be 0, and this will be our maximum negative. I link the points up, and here I have something that looks like a minus cosine graph, which would be the derivative of the minus sine graph, and that is the acceleration time graph. Now, if I can concentrate on the top one and the bottom one, so this is what I'm talking about. I want my displacement time graph and my acceleration time graph. So what I really want is this, and hopefully my drawing has the same period. So this is displacement in meters and time in seconds. Hopefully you can see that A is proportional to minus x. Now what does that actually mean? That this is the mirror image of this in the time axis. Now what does that actually mean? It means that if I was to put an M next to this, you would see that this is a resultant force. So if I push my spring right down to the bottom of its motion here, the force will be directed upwards because the displacement is directed downwards. Here, at the maximum positive amplitude, the force will be directed downwards against the direction of the displacement and towards the equilibrium position. And at the equilibrium position, there's no force at all. So what does that mean in common language? Common language. Layman's terms, it means that the force is always directed back towards the equilibrium position, and the magnitude of that force is the same or is directly proportional to the magnitude of the displacement. It's not exactly the same, there will be a scaling factor. But thanks for listening. The next thing to do is to work on the actual differentiation of this, which is to go from sine to cosine back to sine again, or in the case of the slides on the screen, from cosine to minus sine to minus cosine. So what we're looking at is differentiating the functions that apply to each of these graphs.